All right. So with that said, and that code under our belt, even though that's not going to be something you'll frequently need to code yourself, let's propose now how we might go about building some actual data structures ourselves. The new ingredient here being this reality that if you want to resize a chunk of memory so as to make room for things, we now have that ability. Memory addresses and pointers just give us the ability to like point around at things and move things around in memory. But now that we have malloc and even realloc, you can imagine maybe rewinding, and you could implement that stack, that queue, using not an array per se, because you have to commit to an array size in advance, but if you implement your stack or your queue using a pointer, and then malloc and realloc, and maybe someone else writes all that code for you, perhaps now you can imagine that, OK, now the stack can grow or shrink by using realloc accordingly. You don't have to preemptively say, give me 5 bytes or 50 or 500 or 5,000. You can say, just give me 1 initially. And if I need more, I'll realloc. And if you keep popping things off the stack, you can realloc in the other direction and ask for fewer and fewer bytes. And the operating system can take that memory back as well. So we now have this building block. Let's see what we can do with it. So we've had a few pieces of syntax in recent weeks, all of which we're going to combine now in just a slightly more clever way. So struct is this keyword in C that lets us build our own structure in memory, like a collection of 2 or 3 or more variables, like a person that we've seen before. The dot operator, recall we've used when you do have a struct, like a person, and you want to go inside of it. So like person.name or person.number. And we did this a few weeks ago now. But the dot operator just allows you to go inside of a structure and get the individual variables within. And then the star operator, unfortunately, has a lot of uses now. One was multiplication. Like, my God, that was easy back in the day. Now it's used to declare pointers. It's also used to dereference pointers, so to make one exist and then go to that address. Unfortunately, it's the same symbol for all of those, but it's all related. But with these 3 symbols, it turns out you're going to get one last one today. And my God, it finally looks like the concept. It turns out there's a clever way anytime you want to use the dot and the star together, that is to go somewhere and go to an address and then look inside of a structure, you can actually literally use an arrow symbol on your keyboard. It's not a single keystroke. It's a hyphen and then an open angle bracket. But at least it looks like an arrow. And we'll see indeed in code today, the things I was drawing pictorially on the screen last time with yellow arrows, you can actually now express as well in code. And so here we have our next data structure called a linked list. And this is one of the most useful, powerful concepts in C. It's the kind of thing that you can take for granted in Java and Python and higher level languages. But today we'll see how we or others can actually build these things just using these same primitives. So a linked list is going to allow us to actually do what we used a foam finger for last week, allow us to link together, for instance, these 3 values, maybe with that 4th value over there. And then if there's a 5th, maybe this other foam finger points even farther over way to that 5th value. The key being that you can stitch together fancier data structures without having to like pick all of these up and find new space. You just have to at least connect the dots somehow. We just need to somehow point from one to the other. And that's going to make things much more efficient, it would seem. So how do we get there? So here's my computer's memory as always. Suppose that I'm storing the value 1 somewhere in there, and it's at 0x123 address, whatever. And I'm storing the number 2 somewhere else in memory, 0x456, and number 3 at address 0x789. This is not an array by definition. Why? Even though it's the only 3 things on the screen, what makes this not an array? It's not contiguous. So this violates the definition of an array. But especially since they're sequential, it kind of looks to a human like a list. So it would be nice if there were a data type called list. And there isn't in C. There will be in Python. But you know what? If I could somehow like stitch together these 3 values so I can get from one to the next, then I think we could achieve the idea, the concept of a list, without this really annoying constraint that they all be contiguous as in an array. So how do I do that? Well, at the end of the day, I only have memory at my disposal, right? There's no more training wheels to take off here. This is what we've got underneath the hood of a computer. So if all I have is memory, I think the solution to this problem of stitching together those values in a list must be to spend a bit more memory. That's literally the only resource we have right now. So let me propose that if we want to create a list conceptually out of 3 values that are in random, although pictorially pretty, positions in memory, let me just add a little bit more memory to the picture. So in addition to storing the 1, I'm going to leave myself some room, a little scratch pad, if you will, to use some other bits as well. Same for the 2, same for the 3. And you can perhaps see where this is going based on last week. If I want to somehow connect the 1 to the 2, any instincts as to what I should write in this box here that would lead me effectively from 1 to the 2? What could go here? Yeah? We could store the address of 2. And so specifically, what would you have me write here? Perfect. Ideally, I would just put in this box another integer, one that happens to be represented in hexadecimal. But that's just a base system. It's just a human thing for us to look at. I'm going to put the value 0x456 here. So let me go ahead and reveal that. 0x456 goes there. You can perhaps see further where this is going. Well, if I want to get from the 2 to the 3, I think I need to put below the 2 the address of the 3, which gives me 0x789. Now, if 3 is the end of the list, I don't want to let it be some garbage value, because that would imply that who knows where it's pointing. I need some definitive value. And just what would your instincts be? If I want to make clear with some special sentinel value that the buck stops here, what do I put? What might my options be? Yeah, so null, not NUL per se, but NULL, which was the new keyword we introduced last week, which just represents an empty pointer, if you will. Technically, the address 0x0. So literally the 0 address. And what humans did years ago, they just decided, you know what? Nothing should ever live at address 0 in memory. We're just going to reserve that one special byte to be a special signal, a sentinel value, such that if you ever see a 0 address in a pointer, it just means it's invalid. It does not exist. Now, we write that, though, a little more pleasantly for the eyes as just NULL in all caps. And that's a keyword in C as well. But of course, last week I claimed that who cares where things are in memory? And honestly, like, this quickly gets tedious even worrying about these values. So let me abstract this away and propose that if we want to remember where all of these numbers are in memory, let's give ourselves one final piece of memory that just allows us to start the whole process. Let me allocate on the left-hand side here, not room for a number like 1, 2, 3, just room for a pointer that henceforth I think I'll call list by convention, and then store in that one additional pointer a value that just kickstarts the whole process. This is the sort of treasure map, if you will, that you get handed. And this has the address of the very first actual node in memory. Now, technically, we could just start with this. But it turns out, we'll see, it's just a little cleaner to use a simple single pointer that leads to the things you care about, as opposed to just starting with the first element. Why? Well, if you ever want to get rid of this element, it'd be nice if you could at least still hang on to an empty sheet of paper that indicates that the list is empty, would be one argument for that. So again, who cares about these addresses now? Now, with a wave of the hand, let's just abstract it away. And there are our pointers. Each of those addresses in the squares at the bottom are simply pointing to the next element in the list. The jargon to introduce here would be that now that we have these integers, 1, 2, 3, but they're in these like wrappers, if you will, these structures that have metadata, that is additional data that is related to, but not the data you actually care about. This is data. This is metadata. This thing here, rectangularly, we'll call a node, N-O-D-E. And it's just a term of art that means it's like a container in code for storing some values. This then is a linked list. And this then is the sort of graphical incarnation of like one node pointing to the other. In this case, they happen to be, by chance and by design of this desk, contiguous initially. But there's no requirement that they be such. The 1 could be over there, the 2 over there, the 3 over there. I would just need more foam fingers to point at one to the next. Questions on this concept of a linked list? Yeah, and back. Can you say that again? A good question. Do traditional arrays start with a pointer that's outside of the structure? Short answer, no. Arrays are special in C and certain other languages. And the name of an array is technically a symbol, if you will, that the program knows maps to a specific location in memory. It's just a label, a synonym for a memory address. It does not take up space. So to be clear, the name of an array does not take up space like that extra square on the left. But you do need that extra square on the left when implementing a linked list so that you can determine if the list is of size 0, there's nothing being pointed at, or size 3 in this case. We're sort of taking on more responsibility ourselves. Yeah? How do you point to the next element? Can you elaborate? Good question. If each of these elements is pointing to the next, how does 3 point to the others? Short answer, it doesn't. At least in this design, we have more technically what's called a singly linked list. And as the arrows imply, it only goes in one direction. So if you somehow find in code, maybe a for loop, maybe a while loop, somehow you're sort of in code over here, you have no way in code to go backwards unless we change this to a doubly linked list where I add another box that lets me have arrows in both directions. Or maybe I just kind of make it circular and I connect the 3 back to the 1, which you can totally do. But that tends to make life harder because now you have to figure out when you're stuck in a loop in your data structure. But it's doable as well. But as is, it's a dead end by design. Other questions on this design here? All right, well, how might we implement this structure in code? Well, let me just connect the dots to something like we've seen before here. Like this is how, a couple of weeks ago, we introduced the notion of a person. And we claimed a person might have a name and a number. Last week, of course, we took off some of these training wheels. And a string is really technically a char star in both cases. But really, there's no conceptual difference beyond that. But let's use this same paradigm to implement a node as I described it in that picture. So let me get rid of the name and the number, because that's related only to a person. And let me rename this structure, for discussion's sake, to node. That then invites the question, well, what needs to go inside of a node? Well, minimally, an integer. But this is now where we need to think a little harder, just conceptually, even if you have no idea how to type it at the keyboard, what else needs to be part of a node based on these rectangular pictures that we've drawn? What more do we need? Yeah. Yeah, we need a pointer to another node. So if I don't know how to implement this yet, it could be something like, pointer to another node. How do I do that? Well, you know what? It turns out you would ideally say this. If you know that the next node is itself a node by definition, well, anytime we've needed a pointer, we just use the data type and a star. And I'm going to arbitrarily, but I think reasonably, call this second square at the bottom of those rectangles next as the name of my attribute here. But node star just connotes that the next variable is going to be not a node per se, but the address of a node. And that's exactly what we did. You had me put 0x456, 0x789 in that box, which is the address of another node. So the way we would express this in code would be node star next. But we could call the variable anything we want. Now, this is a bit of a white lie. But we'll fix this right now. This code won't actually compile. C takes you pretty literally, recall. And if you use some term at the top of your file that you don't define until later in your file, you're going to see some error message, right? We've seen this when I've messed up and I forgot to include the function prototypes at the top of my code. This is related in spirit. I seem here on my 1, 2, 3, 4th line of code, I'm trying to use this new term of art that I invented here in my code called node, even though it's a CS term as well. But nowhere above this, it would seem, did I even define what a node is. It's not a data type in C. Every computer scientist knows what a node is, but it doesn't come for free with the language. So I need to do something else. Like I need this word here to come first so that I can use it here. And so we have this sort of catch-22. Like how can a structure be self-referential, that is, point to another version of itself if the word doesn't yet exist? So the solution to this in C, which we didn't need for a person, because there was no notion of connecting as a list, we need one more keyword here that we didn't need for a person, and we reuse that keyword here. So kind of an annoying detail, but if we preemptively call this whole thing struct node, you can now refer to the thing on the inside as a struct node star, but then you can shorten the name of the whole thing from struct node to just node. Sort of an annoying sequence of steps, but in short, anytime you're building a node, a linked list in memory, this is just the paradigm. You use typedef, struct, the name of the thing you want to define, like node. You use that name on the inside if you want to point from one to another, and then you can shorten it down here to just be called node. Questions then on this code here? Questions on what we just did? Well, if I rewind just a moment to that final picture, what would be the upside, to be clear, of having jumped through these hoops and added this complexity, if you will? What problem did we just solve by linking together these three values, to be clear? Yeah? Making lists that are not contiguous, if you will. So making lists that are not contiguous in memory, the upside of which is that if I want to add the number 4 to this list, it looks like I could choose from any chunks of available memory on the screen. I just need to sort of point from the end of the current list to wherever that other one is in memory. What I don't need to do, to be clear, is copy the 1, the 2, or the 3. Everything can just stay put, which means time-wise, I can do this much more quickly, it would seem, without copying things again and again, and even without using realloc to let it do all of the copying potentially for me. All right, but as we'll start seeing even more in the coming weeks, every time we benefit and solve some problem, we pay a price. There's a trade-off. What is a downside, as you might perceive now, of using a linked list instead of an array? Yeah? Yeah, I mean, we use twice as much memory because now, in addition to storing the integers 1, 2, 3, I also need to store a pointer for each of those. And honestly, even this picture is a bit of simplification. Technically, in most systems today, each int would be 4 bytes. Technically today, most pointers, though, would be 8 bytes. I just didn't want to draw this weird shape on the board where the bottom square is even bigger than the top square. But technically, we're using even more than twice as much space for these pointers. So there's that trade-off. Now, thankfully, decades after C was invented, memory is generally much cheaper nowadays. And so it's OK to sort of spend more of it if you need to. And it depends on what you want to optimize for. But that's absolutely here a downside. What's another downside of having transitioned to a linked list? You can't index into it. Now, I haven't even tried in code, but when you have a linked list, you can no longer use square bracket notation. Because why? Well, square bracket notation just assumes the contiguousness of memory. Location 0 is here. Location 1 is literally 1 to the right. Location 2 is literally 1 to the right, 1 to the right. These things, even though I've drawn it from right to left to just keep things pretty, there are gaps here. And this is just my interpretation of this. These gaps could be big. They could be narrow. They could be down here, up here. They could be anywhere so long as we're linking things together in this list. The computer can't just use bracket 0, bracket 1, bracket 2 anymore because it can't do simple arithmetic and jump to like the middle. And now here's perhaps the worst price we've paid. If you don't have square bracket notation, or really you don't have contiguousness, what algorithm did we just sacrifice for this dynamism? If you rewind even back to week 0, and we gave it a name in week 3, what algorithm can we not use now if we can't assume that the memory is back to back to back to back? Binary search. Why? Because binary search, just like the phone book back in the first week, requires being able to arithmetically jump right to the middle. Right? Take the total length of it, divide by 2, and boom, you're right there in the middle with some simple arithmetic. Here, they might be laid out, again, with these big or small gaps. There's no simple math I can do to just jump immediately to the one in the middle. And in fact, again, if this TV were bigger, the 2 could technically be in memory, be way down here, or even way over here. The foam finger could be pointing in any number of directions, depending on where malloc put the thing. There's just no way to do binary search. And so it would seem that we've paid another price, indeed, in terms of its performance. We're now talking about linear time again. So that's a regression. Now, that's also a lot. Feels like a good time for some muffins and fruit out in the lobby. And when we come back, we'll try to solve the problem we just created. So see you in 10.